Bonjour, aujourd'hui on va apprendre des deep learning, de l'apprentissage profond. Just kidding, I also speak English, it's going to be fine. So, yes, so my sister will be learning deep learning with me today.
Yeah, I don't know anything about it, so let's see.
Okay, so. Mm, So here's a tutorial. Um, oh, okay. So this is all in Spanish, so I guess we'll translate for you. So this is like a course on deep learning by interactivechaos.com, making things simple apparently. So it says introduction. The discovery uh, by the ends of the 19th century uh, of the brain of living beings not being a uniform nervous mass, but one that was composed by independent units, neurons, led to numerous scientists to try to emulate the behavior of the human brain using mathematical structures. The artificial neuron of McCulloch-Pitts from 1943 and the evolution of these was introduced by Frank Rosenblatt in 1956, the so-called perceptron, supposed the seed of the actual artificial neurons. It was rapidly seen that the power of calculus from these structures was a lot greater when they worked connected to each other, forming the so-called neural artificial networks or artificial neural networks, in which the artificial neurons are situated usually in parallel layers in such a way that the generated data um, in such a way that the data generated by a layer is the data from which the next layer is fed. As soon as the technological development allowed it, artificial neural networks from the 20th century gave step to the so-called deep neural networks, or redes neuronales profundas in Spanish, characterized for including a high number of parallel layers. Obviously, the concept of high number has varied over time. So, in a sense, any network with two or more layers was already renowned deep or profunda in Spanish. Profound, yes. Nowadays, neural networks are formed by dozens or even hundreds of layers. As an example, the network Inception ResNet v2 used in artificial intelligence has 572 layers, although strictly speaking, not all of them are formed by artificial neurons. The area of knowledge dedicated to these deep neural networks is known as deep learning, or deep learning in English. So yeah, the deep learning has revolutionized our society. Wow, AI, the TikToks, the magic green screen that takes off the background of your shitty neo-tard post guard brain rot on what was I gonna say? I saw at Walmart the other day a little tiny toilet that said "Skibidi Toilet." Yes, that's the level of brain rot we've gotten with some of the artificial intelligence out there. And you know, you collect these items like inside the toilet, so you don't know which one you're gonna get. Oh yeah, I love gambling with kids. Yeah. Um. So yeah, it says deep learning has revolutionized our society. Even when this technology is frequently unknown to the great public.
To the general public.
Yes, to the general public, thank you. But great. It would be great if we use the word great a little more. Um, well, it's the one that gives the shitty support in virtual assistants that we all have in our mobile devices. It's the one that's allowing the development of 100% autonomous cars. The one that's revolutionizing medicine, allowing to classify tumors with high precision, analyze clinical images, or diagnose or medically or automatically and medically diagnose. For just citing a few of their applications. So, okay. So, okay. Oh, we actually skipped a page, but whatever. Like, this is the first page. Yeah. It doesn't say shit, but whatever. Well, it does say something. Tutorial in development. So, whatever. So the nervous system. So before checking out the mathematical models that have been developed based on the brain structure, it's important to briefly go over the way neurons work. These are the main component of the nervous human system, being specialized in the processing and transmission of cellular networks. Of course, cellular literally meaning like cells, like not like telephone cellular signals. Or maybe in the future they will also be cellular signals. Who knows?
Who knows?
Could you say that again?
Who knows?
Okay, yeah, I think the audio does pick up your voice barely. It says grosso modo. How do you say grosso modo in English?
Grosso modo. No sé. ¿Verdad? De
by and large, no. Um, all in all, we can distinguish in them four principal parts, four main parts. So we have the dendritas, the soma, the axon, and the synapses. Would you like to fill us in, Jimena? No? You know something, a little something about biology, don't you?
Not enough, but I think that's the axon. An axon is an axiom.
Oh, yeah, that makes sense. So the dendritas are extensions with branches from which the neuron comes.
Branches that lead to the neuron.
Branches that lead to the neuron.
I don't know.
That. They are
like entry signals for the neuron.
Yeah, so they're extensions with branches by which the entry signals are sent to the neuron.
Yeah.
So those are the dendritas, whatever that means. So they're like the ones that send input signals. Most of them. Most of the input signals.
Receive. They don't send it, they receive the input signals.
From what I understand, they receive them and then they send them to the neuron.
Yeah, I guess so.
I guess they're senders and receivers, maybe.
Isn't like the... I guess.
It's a little vague,
you know. Yeah, it is.
So the soma is the neuron's body. Okay, yeah, so it does look like a body. And then the axon. It is a, well, I guess we could say a highway that drives the electrical impulses from the soma to the axon terminal in which the synapses are located. And the synapses are structures that allow the neuron to transmit the signal to other neurons. Wow. Cool. Cool.
Cool beans.
So the communication between neurons implies an electrochemical process in which once the neuron is excited above a certain level due to incoming electrical signals, it transmits through the axon a signal that excites other nearby neurons, that is, the ones that are adjacent.
And so on and so on.
And so on and so on. That's y así sucesivamente. The doctrine of the neuron. Who the fuck starts sentences with sin embargo? Like, who wrote this?
Literally.
I mean,
literally.
Okay. Would you care to pitch in as you're a yapper major?
Yeah. No, I wouldn't start with sin embargo.
I mean, yeah, sin embargo is like nevertheless.
Yeah.
Right? In English, yes.
Nevertheless.
Nevertheless what? Like,
Mm-hmm.
yes, okay. So maybe he was fixing something up and he just deleted a paragraph out of nowhere. Said this is a piece of shit. So, anyways, maybe it's not. It probably isn't. I mean, it really doesn't matter if it starts with nevertheless.
Maybe they thought like están intentando hilar como que lo anterior, ¿no?
Yeah, that's.
Like they're trying to pick off from the last page, but still that doesn't make sense really.
Yeah, no.
Well, let's read on.
Okay, so the neurons doctrine. Nevertheless, up until the late 19th century, the brain was interpreted as a
Continuous
yarn.
membrane. No, membrana, tejido. Tissue.
Okay, yeah. So, nevertheless, up until the end of the 19th century, the brain was interpreted as a continuous, what was it?
Tissue.
A continuous tissue um, formed by only a network of nervous cells. Blessed be you.
Danke.
In 1888, Santiago Ramon and Cajal published an article that explained that nervous cells were not continuous in the brain of birds, which led to the so called neurons doctrine, or doctrina de la neurona in Spanish, based on the hypothesis that the neuron was effectively the functional unit of the brain. So this is Santiago y Ramón Cajal. Strong name. So Ramón y Cajal would share in 1906 the Nobel Prize of Medicine with Camillo Golgi. Quote, in honor of their work about the structure of the nervous system, unquote. Weirdly enough, Camillo Golgi defended the so-called reticular doctrine, opposed to the one developed by Ramón y Cajal. Weird. Okay. So the discovery of Ramón y Cajal opened the door for new investigations and development of logical and mathematical models that would simulate the behavior of biological neurons, being the most prominent the so-called McCulloch-Pitts model. So the McCulloch-Pitts model. Even when this model is not so known as the others that followed it, like the one developed by Frank Rosenblatt, the truth is that he placed core stone over which the current concept of neural networks and deep learning has been developed. So I guess he's a pretty important guy. So Warren Sturgis McCulloch. Warren Sturgis McCulloch.
Dr. Sturgis.
What?
Like Dr. Sturgis from Sheldon, young Sheldon.
Oh yeah, they're probably related or something.
Mm-hmm.
Cool. Yeah. So for the ones who don't know, Dr. Sturgis plays an important role in Sheldon Cooper, fictional character from the Young Sheldon and the Big Bang Theory universe.
Correct.
So Warren Sturgis McCulloch, born 1898, died 1969, was a neurologist and cyber
Medic.
cyber guy, and he was American. He studied philosophy and psychology. In 1941, after an internship at the Bellevue, New York hospital, he started working at the Department of Psychiatry in the University of Illinois in Chicago. It was during this period when he met Walter Pitts. So, Walter Harry Pitts. Walter Harry Pitts, born in 1923 and died in 1969. Are you going to the bathroom?
No, it's a coffee.
Okay. So we really don't have any viewers, so
It's okay. Let's keep going. Go on.
so what?
Go on.
So Walter Harry Pitts, born 1923 and died 1969.
So his pits are hairy.
Maybe they are. Was probably what we would call today a special guy. At the age of 12 years old, he spent 3 days at the library reading the Principia Mathematica. This is a document by none other than Russell and Whiteheads, or no, maybe it's
I don't have the book. No.
by Alfred North Whitehead and Bertrand Russell, FRS. And here it says it's a book by Isaac Newton, but I really don't understand. Okay. So it says here that it's
Series.
a series of 3 books published between 1910 and 1913 by Bertrand Russell and Alfred North Whitehead. And then he
Wrote. Wanted to.
he had the balls
Mm-hmm.
to write to the first of them pointing out what he considered serious problems found in the first half of the first volume.
You know, that sounds like something Sheldon would do.
Yeah,
You
it
know,
does.
he really would do that.
Yeah, I guess so. So, when Bertrand Russell moved to the United States and started teaching at the University of Chicago, Pitts, um, being 15 years old, started assisting his classes without formally registering as a student. Russell um, tried to convince Pitts to study with other mathematicians at, from the university, which he did. Nevertheless, it seems that Pitts did not uh, have the wealth nor a place in which to live.
The means.
Oh, yeah, income means whatever. So, how do you translate el encuentro?
The meeting.
The rendezvous.
Mm-hmm.
So, yeah, the meeting.
I don't know, because like a rendezvous is like an established meeting, but this is like you found each other.
Maybe, yeah.
You know.
McCulloch moved by the by Alan Turing's demonstration of his machine, what we know today as Turing machine, was capable of solving um, any mathematical problem that could represent itself as an algorithm. He set himself to demonstrate that the Turing machine could be used also through a finite set of structures that would model the behavior of biological neurons. So this is Alan Turing. If you don't know him, at 16 years old, seeing as McCulloch saw potential of in Pitts and the shared visions that they shared about the functioning of the brain. So yeah, I really narrated that very stupidly, but
the visions that they shared.
Seeing as Pitts had a lot of seen potential by McCulloch and the shared visions that they shared in respect to the functioning of the brain, in the first half of 1942, McCulloch invited Pitts to live with him and his family, period in which both of them collaborated in the preparation of the article that, published in 1943, would define his neural model. Wow. So finally, McCulloch Pitts neuron. The article, a logical calculus of ideas immanent in nervous activity, that you can download here. The URL. McCulloch and Pitts presented a model that approximated the behavior of biological neurons. The authors take off from five hypotheses. Um, so the five hypotheses go as follows. Number one, the activity of the neuron is a process all or nothing. Interesting.
Only on and off, no in between.
Cool way to view the world. Let's all become radical extremists. Number two, they should excite themselves as a certain number of synapses within the latent addition period to excite the neuron at any moment. And this number is completely independent of the previous activity and the position of the neuron.
Mm-hmm.
Number three, the only meaningful delay within this nervous system is the synaptic delay, or retardo synaptico. That sounds something like Hermione would say.
Retardo synaptico.
Retardo synaptico.
Tardy synapse.
Yes, tardy synapse. Number four, the activity of any synapses. What?
Late synapse. Tardy synapse.
Yes, the late, tardy, retard synapse. Number four, the activity of any inhibiting synapses. The activity of any inhibiting synapses completely disallows the excitation of the neuron in that moment. Number five, the structure of the network does not change with time. That's the dumbest thing I've ever heard so far. Do you agree?
Structure of the network does not change over time.
Yes. I think it does. Maybe I'm wrong. I'm not a neuroscientist. So, the hypotheses in English are as shown. We shall make the following physical assumptions for our calculus. Number one, the activity of the neuron is an all or none process. Number two, a certain fixed number of synapses must be excited within the period of latent addition in order to excite a neuron at any time, and this number is independent of previous activity and position on the neuron. Number three, the only significant delay within the nervous system is synaptic delay. The activity of any inhibitory synapse absolutely prevents excitation of the neuron at that time. Number five, the structure of the net does not change with time. From these hypotheses, three of them, number one, number two, and number four, are the ones that most clearly characterize the so-called McCulloch-Pitts neuron. Let's see them one by one. The hypotheses, not the models. So all or none activity. This first hypothesis supposes that both the signals that are received by the neuron as well as the generated signal are going to be of type binary, a boolean, a 1 or a 0. Are you a 1 or a 0, Elliot?
Hmm.
You do or you do not? Are you a 1 or a 0?
One.
A 1. Okay.
You?
I don't know. This supposes that the neuron is a binary function that transforms a set of Boolean values into another Boolean value. Wow. Excitation of a set number of synapses. This second hypothesis assumes that the McCulloch-Pitts neuron will have a threshold associated, that is a fixed threshold that will determine the degree of excitability of the neuron. When the number of exciting signals equals or surpasses this threshold, the neuron will get excited and will generate a signal value of 1 that will be transmitted to the next neurons in the network. So in Spanish we have next for a singular subject and a next for plural subject. But I guess in English it makes it easier. A conclusion that we can arrive at is that if the threshold is superior to the number of input signals, the neuron will never get excited and will generate a signal of value 0 forever. So, inhibiting synapses. Last but not least, this hypothesis assumes that if the neuron receives any inhibiting signal, the output of the neuron is going to be always 0. And this is all independently of the rest of the signals that could be arriving to the neuron. Interesting. So it's like an off switch. Could you stop being on your phone here? You're learning something.
Okay, continue.
Thank you. So the behavior of the McCulloch-Pitts neuron. We can sum up what we saw in the following way. The neuron is going to have a set threshold that will determine its excitability degree. The incoming signals have all the same weight. The neuron is going to sum the incoming signals. It's going to add them up. If the obtained value is equal or superior to the threshold, a signal of 1 will be generated. If that is not the case, the result being the result of the sum inferior to the threshold, a zero signal will be generated. All of this is if there are no incoming inhibiting signals. If there were, the signal generated by the neuron would always be zero, 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 null, nil. Representation of the McCulloch-Pitts neuron. The authors did not include in their article any diagram that would represent their artificial neuron model. Nevertheless, it results very convenient to do it, and we can see right here. Okay, so we have theta, y, x1, x2, x3, and x4. Cool. So my guess is y is the output, theta is the inhibiting signal, and all the x's are input values. Do you agree?
Yes.
So in this diagram, we're representing a neuron with 4 entry or input signals: x1, x2, x3, and x4. These signals can be exciting signals or inhibiting signals, and their values could be 0 or 1. If it's about an inhibiting neuron and it takes the value of 0, it is ignored. On the contrary, if it takes the value of 1, the output of the neuron will always be 0, as we've seen with the inhibiting neuron. The neuron also has a threshold associated and excitability threshold associated called theta, and the output signal is represented with the letter Y. Wow, I'm a magician.
Wow.
As we've seen, the behavior is the following. If any of the XI signals is inhibiting, that is x1, x2, x3, and x4, if any of them is, the Y signal is going to be 0. Ignoring all the input signals. If that's not the case, the neuron will sum up the input signal values. The result of this sum is going to be compared with the threshold theta. If it's equal or greater than this, the neuron will emit a value, a signal of 1, a signal value of 1, or a value signal of 1. And on the contrary, it will emit a value signal of 0. The activation function. This last conversion, the one that converts the result of the sum of the inputs into a 1 or a 0 based on the fact of reaching or not the exciting threshold, the excitation threshold of the neuron, it's what is known as the activation function, because, well, it determines if the neuron's activating, that is generating a signal of 1, or not, which would be generating a signal of 0. We can represent this function in the next graph. So here we have a weird graph. A bunch of zeros on the y and then ones here. So the horizontal axis represents the result of summing up the input signals, and the y and the vertical axis represents the signal um, emitted by the neuron, that is, the output. In the example of the image of the previous image, the neuron has a theta threshold equal to 2. In what image? Okay. Maybe they skipped an image. Okay, in this way, when the sum of the neurons, of the input neurons, is 1 or less, the output signal of the neuron will be 0. And when this sum is 2 or more, the output signal will be 1. This function is usually called step function, because it implies more or less this: a value of 0 is constant until a certain value m, and from then on it's a 1 value. This step function is usually represented like this: step function. Let it be noted that in this case, the vertical segment shown in red does not really have any sense at all. The generated signal by the neuron will never take the corresponding value to none of these points, that is, between 0 and 1, excluding the limits of the vertical axis. It's going to be either always 0 or a 1. Are you a 1 or a 0, Elliot? The correct representation will be the following. So here we have a discontinuous function. And also it looks better. Kime? ¿Ya? Alternative representation. We can then represent the McCulloch-Pitts neuron with the next diagram. So here we have a sum and an X with a line over it. So in the previous image, so like in this image, one of the signals has been separated. Some effects representing the possible inhibiting active signals that could exist. It's irrelevant whether there is one or many, um, because the neuron will behave itself um, the same way in every case, um, outputting a signal of 0. In this way, we're assuming that the rest of these signals xi are exciting signals, and the interior of the neuron and in the interior of the neuron, uh, two functions are shown that are applied to the data. That is the sum of the signals, of the input signals, that is, and of course the activation function that transforms the um, previous value into a 1 or a 0 based on whether the excitability neuron threshold theta is achieved. Continuous non-continuous function. Let it be observed that the first of these two functions that is applied to the data sums these input signals. It's continuous. No, I think this is not the word. Hmm. Oh yeah, a linear function. Okay, no, so forget the title that I said. I should have said linear nonlinear function. Let it be seen that the first of these two functions that is applied to the datum, that is the sum of the input signals, is a linear function. A linear function. Linear function. That is the sum of the input values. While the second function, the step function that transforms the previous sum into a 1 or a 0, is a function, a non-linear function. This combination of linear and non-linear were the big part of the calculus potential is of the artificial neurons. Boolean functions. The McCulloch-Pitts neuron woke up rapidly the interest of scientists, as it would allow to simulate the behavior of Boolean functions. Let's see some examples. The AND function. The AND function that returns the value 1 only when all the entries are also 1 is immediate. If we have two exciting inputs, if we have two exciting inputs it is enough that the neuron threshold be equal to 2 for the generated uh, output to take the value of 1 only when both inputs also take um, the said value, that is 1. So this is the truth table. So yeah, theta is 2. So this is 1 and this is 1. 1 plus 1 is 2. Wow. So that gives you this. And any other thing gives you this 0. OR function. The OR function that returns the output of 1 when any signal when any input signal is 1 is also very easy to obtain. It's enough, it's just enough, it is only sufficient that the theta value take the value of 1, so that whenever there is an exciting signal of value 1, the neuron activates. So any of the inputs is 1, it will always be 1, including when both of them are 1. The NOT function. To recreate the NOT function that returns 1 when the input signal is 0 and vice versa, it is sufficient to send the input signal as an inhibiting signal along with a second input signal that always takes the value of 1. The neuron's threshold shall always be 1 or less. That is, if the inhibiting signal takes the value 0, the neuron will ignore it and it will return the value of the second input, and when it equals or surpasses this threshold. On the contrary, if the inhibiting signal takes the value of 1, the answer of the neuron will always be 0. Cool. Cool, cool, cool. So a NOR function. The NOR function, in which the output is 1 only when the inputs are equal to 0, can be emulated with 2 neurons, the first simulating an OR gate and the second feeding itself from the output of the first one, simulates the NOT gate. So OR plus NOT is NOR. Yay. Geometric interpretation. So with the examples that we're watching, in which the neuron has 2 inputs, x1 and x2, that take values 0 or 1, let's consider all of them exciting inputs. We can represent in the plane the 4 possible combinations of values: 0, 0, 0, 1, 1, 0, and 1, 1. we pay some attention, the result of adding up set values and comparing the result with the neuron threshold allows to separate the um, points in the plane in two blocks, delimited by the segment formed by those points of the plane that sum up the value of the threshold. Cool. Threshold 0, true function. For example, if the threshold is 0, we would be defining a line formed by only those points in which the sum of their coordinates x and y be 0. In this case, the four possible combinations of x1 and x2 that would in this case the four possible combinations of x1 and x2 would be on top of the segment or above it, which means that for this threshold any of the combinations will provoke the activation of the neuron, generating a signal of 1. Threshold of 1, the OR function. If we set a threshold of 1, the division of the points in the plane is represented as follows. So here the 0, 0 is not present, but as you can see the 1, 0 is present and the 0, 1 is present. And of course the 1, 1 is above the line, so it also is part of the inputs that would generate a 1. So yeah, those are the green points, and anything that's below it will generate a 0, and anything on it will generate a 1, and anything above it will also generate a 1. That's pretty much it. Threshold 2, AND function. If the threshold is 2, the only combination that is on the segment or above it is the one corresponding to the input values 1 and 1. So yeah, 0, 1 will not be in or above the segment, and 1, 0 will also not be in or above the segment, and 0, 0 of course will not be part of it. So there are some other elemental cases that the threshold be less than 0, that it be greater than 2, or that there be an inhibiting active inhibiting signal. So a threshold less than 0. If the threshold is less than 0, the emitted signal by the neuron will always be 1. That is, the neuron would always be active, because the sum of the entry signals or the input signals would always be equal or greater than the threshold. Let's remember that input signals only take values 0 or 1. So in the next diagram, we show that the result for a neuron with a threshold of -1 um, of course has the four combinations of input values that would output the 1. That's because all of them are above this segment. So a threshold greater than 2. In this other case, the emitted signal by the neuron will always be 0. That is, the neuron would never activate because the sum of these input signals, assuming that we're working with a neuron with only 2 input signals, would always be below the threshold. In the next diagram, we show the segment for a neuron with a threshold of 3. We are we are demonstrating that none of the combinations of the input parameters equals or surpasses the threshold. Active inhibiting signal. Last but not least, we know that if any inhibiting signal would take the value of 1, the neuron would generate a signal of 0. That is, it wouldn't activate, and this independently of the values of the other signals. So the threshold selection. So from these we can see that the McCulloch-Pitts neuron behaves as a classifier that separates the points of the plane in 2 blocks in function of what the threshold chooses. We're demonstrating that the line that separates both blocks will always be a segment which impedes applying this method of classification to non-separable lineal scenarios. For example, let's take the XOR function, that is OR exclusive, like only one input produces a 1 and both of them produce a 0. This function returns the value of 1 when one of them has a value of 1, but it returns 0 when all of them take the same value, be it 0 or 1. Taking these combinations to the plane, we have the next representation. Unfortunately, we demonstrate that there is no segment capable of separating these 4 points the same way that the function does. So yeah, the McCulloch-Pitts neuron does not allow to simulate any logical function.
It was a pleasure.
I think you're skipping the lecture.
Sorry, I need to sleep.
So again, the limitations of the McCulloch-Pitts neuron. So some of the limitations are it only allows Boolean input. All of them have the same weight. The output is also Boolean. The activation function is always a step function. It is not possible to simulate um, anything that isn't linear separable linearly or linear separable. So for example, it wouldn't be possible to simulate the XOR function. Um, Another limitation of the work developed by McCulloch and Pitts is that they didn't specify a method for the configuration of the neurons. That is, if we have a set of neurons connected through each other forming a network, and for a certain set of values, of input values, we want the output um, be a 0 or a 1. How should we configure the neurons? This process of configuration is what we know nowadays as training, the neural network training process, which was not defined by these authors. So yeah, it's pretty important. This artificial neuron was pretty important in the development of current neural networks. So Heb's learning. In 1949, Donald Hebb, born 1904, died 1985, Canadian psychologist, revolutionized the way in which artificial neural networks were understood. That's Donald. Hey Donald. So, in his book, The Organization of Behavior, he proposed that what would today be known as Hebb's rule, which can be summarized in the following way. Let's suppose that the persistency of a repeated activity or signal tends to induce changes, that is, cellular changes and lasting changes that promote its stability. When the axiom of cell A is close enough as to excite cell B and repeatedly takes part in the activation, processes of growth or metabolic change occur in one or both cells in such a way that the efficiency of cell A as the excitable capacity of cell B are augmented. That is, when a neuron tends to activate another one, the weight or the importance of that connection between those both neurons augments. Proposal that proves the basic learning algorithm through artificial neural networks. This rule usually can be summarized with the phrase neurons that activate together stay together. Even though Hebb insisted on the idea that the first neuron should activate before the second one, or a relation of causality should exist for said connection to suffer the mentioned change. Um, so, if it were desired for the McCulloch-Pitts neuron to be capable of supporting this proposal, the links that get to a neuron should have an associated weight that should be able to change to adapt adequately to the relationship of both neurons. This learning um, is called, well, this, hmm, so this approach is called Hebb's learning, or Hebb's approach, I guess. So Frank Rosenblatt perceptron. Another very important and frequently the most known in the development of the neuron is the one made by um, Frank Rosenblatt. That is the development or of the perceptron in the period of 1957 to 1962. So Frank Rosenblatt, born 1928, died 1971, was an American psychologist born in New York who was considered one of the fathers of neural networks. Hey Frank. That's a very 1940s hair. Nice tie. They're like leaves from a maple syrup tree. He is primarily known for the development of the perceptron, an electronic device built based on the of the biological principles and that was capable of learning from data. Unfortunately, he died at 43 years old in 1971, the same day of his birthday, in a boat accident. Well, so the perceptron. As part as a part of his investigation on the functioning of the human brain, Rosenblatt introduced the perceptron in an article published in 1958. The perceptron, a probabilistic model for information storage and organization. Article that you can download here. Interesting. That's a long paper. In his research based on the McCulloch-Pitts neuron and the Hebbian learning, even though heavily influenced by the works of mathematician John von Neumann, Austro-Hungarish, and the doctor and neurologist William Ross Ashby, English. John von Neumann and William Ross Ashby. In the document, Rosenblatt presents his perceptron in the following way. The theory has been developed for a hypothetical nervous system or machine called perceptron. The perceptron is designed to illustrate some of the fundamental properties of intelligent systems in general, without catching up too much in the uh, special and frequently unknown conditions of biological and specific organisms. The analogy between the perceptron and biological systems must be evident to the reader. Implementation in IBM 704. The initial objective was the construction of a classifying machine, of an image classifying machine capable of learning from the Hebbian point of view. Um, Unfortunately, well, no, in this case, the first implementation was made um, in a program executing in an IBM 704 at the University of Cornell a year before the publication of the aforementioned article. So the Mark I perceptron. It wasn't until 1962 that Rosenblatt got the necessary um, means to implement his perceptron in a machine that received the name of Mark I perceptron. Mark I perceptron at the Aeronautical Cornell Lab, Division of Rare and Manuscript Collections, Cornell University Library. Operation Manual. Ahead are just for curiosity the first chapters of the introductory manual of operations of the Mark I perceptron, as well as the photograph of said page. The Mark I perceptron, reference 124, is a pattern learning and recognition device. It can learn to classify plane patterns into groups on the basis of certain geometric similarities and differences. Reference 4. Among the properties which it may use in its discriminations and generalizations are position in the retinal field of view, geometric form, occurrence frequency, and size. If of the many possible bases of classification a particular one is desired, it can generally be transferred to the perceptron by a forced learning session or by an error correction training process. If left to its own resources, the perceptron can still divide up into classes the patterns presented to it on a classification basis of its own forming. Interesting. This formation process is commonly referred to as spontaneous learning. The Mark I is intended as an experimental tool for the direct study of a limited class of perceptrons. It is sufficiently flexible in configuration and operation to serve as a model for any of a large number of perceptrons possessing a single layer of non-cross-coupled association units. This manual is intended primarily as a guide to the setting up and operation of the machine. It does not require extensive familiarity with the theory of perceptron systems. For those familiar with the theory but not necessarily concerned with actually operating the machine, the manual should serve to indicate the machine's potentialities as a research instrument. Image classification. As it was already mentioned before, the Mark I perceptron was designed to function as an image classifier. Um, with this objective in mind, it included a set of 400 photo sensors distributed in a 20 by 20 matrix. It is as if it analyzed images of 20 by 20 pixels. To train the machine, the operator had to show it the machine to these photo sensors. The perceptron shown in the aforementioned image is was, for example, training to distinguish photographs of men and women. After analyzing the uh, photograph shown by the operator, the perceptron made its prediction, and the operator indicated to it via some switches whether it had um, succeeded or failed. The weights of the links were controlled um, through potentiometers, and on the basis of whether the answer, the given answer, were right or wrong. Some motors updated these weights. The aforementioned images were extracted from a documentary available on YouTube. So this is a documentary. Perceptron research.
In the 1950s and 60s, scientists built a few working.
Cool. So, basic organization. The Mark I perceptron was divided into three blocks: sensorial units, that is S units, associative units, A units, and response units, that is R units. Cool. Cool, cool, cool. Basic organization of the Mark I perceptron. Source: Manual of Operations. The signals were transmitted from left to right, from the sensors to the response units, through the random connections, just as is shown in the aforementioned diagram. All the units, with an independence of its own, were configured in such a way that they were activated and transmitting one signal only when the sum of the input signals surpassed a certain threshold. The input signals of the sensorial units were luminescent. The signals were the signals captured by the photosensors, and the rest of the units were electric. The next image shows a white and black image of a black and white image of the Mark I perceptron and the zones in which it was organized. Cool. Figure 2, Mark I perceptron. Basic organization of the Mark I perceptron. Source: Operations Manual, or Manual of Operations. Frank Rosenblatt's neuron. Frank Rosenblatt's neuron implied a certain kind of units or neurons that we could schematize in the next diagram. So we have the input signals, the synaptic weights, the summing union, and the activation function, and the output. Wikipedia image. Unlike what happened with the McCulloch-Pitts neuron, this neuron had a weight associated to each of the input links. That is, the weight by which the value of the input signal would be multiplied before it reached the link. After that, all the signals were summed up and if the result exceeded a certain minimum value, the threshold of the neuron would return a signal of 1, and if it did not, it would return a signal of 0. So this is just a step function. That is the result of the ponderated summations of the input signals that were applied using a step function. If said result surpassed the threshold represented by theta in the previous image, the response of the neuron will be 1, and on the contrary, the response will be 0. Yeah, this is the same behavior as in the McCulloch-Pitts neuron. If we want to express this as a mathematical model in algebraic terms, we could do it as such with the following expression. So output equals to output is going to be 1 if the sum of the input signal times the weight is greater than the threshold, and on the contrary, it's 0. So this type of neuron is what we know today as a perceptron, which should not be confused with the mechanical design that Frank Rosenblatt developed, which received the same name, unfortunately. So utility of the artificial neuron. These types of structures allow us to make predictions, take decisions as we can see fit. So let's put a simple example. Let's imagine that we want to decide whether to buy a home, and let's use 3 factors. If the price is good, if the house is close to the beach, and if it has a garage. And all of these factors are either a 1 or 0. 1 if it is, or 0 if it isn't. So nice house. So given a concrete house, in function of the values that we give to these 3 factors, we will decide whether or not to buy the house. For example, let's say we want the price to be good, so we give it a weight of 3. that we care a lot that it's close to the beach, so we give it a weight of 6, and that we are thankful that it has a garage, although we could live without it. So the factor we will give to this one is 2. And let's say that we want once the 3 factors are evaluated, consider a house as decent of our attention if the sum of the 3 evaluations supersedes or equals the value of 5. With this configuration, we have weights of 3, 6, and 2, as well as a threshold of 5. It will be enough for a house to be close to the beach. So it would be enough for a house to be close to the beach to for us to be content with its sale, and this independently of the other values, because 0 times 3, that is the supposed price, plus 1 times 6, the proximity of the beach, plus 0 times 2, the garage, sums 6, which is greater than or equal to 5. But even if it weren't close to the beach, we could also buy it if the price were good and if it had a garage. So 1 times 3, the price, plus 0 times 6, the proximity of the beach, plus 1 times 2, the garage, equals 5, which also equals or exceeds our threshold of 5. In any other case, the sum of the values would not reach 5. So our decision wouldn't be to buy the house. Also, of course, if you join these 2 and these 2, it does give higher than 5. So I think he means like in any other negative case. So if we change the neuron's configuration, modifying the weights or the threshold, its behavior would be different, giving us completely different predictions to the same input data. So they're pretty important. Of course, the really useful thing of an artificial neuron is not deciding of arbitrarily its weights and its threshold, but training it, giving it lots and lots of examples of configurations of houses and the associated decision whether we would buy it or not, and letting the neuron decide the weights and threshold adequate with the objective of later applying our neuron to the data of another house and let the neuron tell us whether we should buy it or not. Limitations of the Frank Rosenblatt neuron. The development of Mark Rosenblatt, that is the perceptrons, supposed a kind of architecture that would be known today as feed-forward neural networks, which in Spanish could be translated as redes neuronales prealimentadas. although in this tutorial they will be mentioned mixing both languages. Redes neuronales feed-forward, redes neuronales de tipo feed-forward, or feed-forward neural networks. And in this architecture, the signals or display are moving in only one direction, from the input of the neural network to the output, without forming any kind of cycles. The perceptron of the Mark Rosenblatt's perceptron was of this kind, but it was based on a single layer of units or neurons willing to be in parallel. These perceptrons of only one layer were only capable of classifying data linearly separable, which limited enormously its capacity of learning and prediction. In 1969, two researchers, Marvin Minsky and Seymour Papert, published a book called Perceptrons, in which they showed how these kinds of neural networks were incapable of implementing the XOR function, as well as other limitations of these kinds of artificial neural networks. So this is Marvin Minsky and this is Seymour Papert. The Winter of Artificial Intelligence. The publication of this book promoted a decay and disinterest in financing available for the investigation of and research of neural networks. Something similar occurred in other near research, such as automatic translation, area in which, after very promising starts as the automatic translation of from Russian to English made in 1954 and known as the Georgetown experiment, the publication of the ALPAC paper in 1966 set on manifesto the real limitations of the technological development at the time, and that the artificial intelligence was suffering. So all this led to the period known as artificial intelligence winter, period that started at the end of the 60s and extended more or less 10 years into the start of the 80s. So this decline in research lasted until the potential was recognized. This would suppose neural networks feed forward with two or more layers, now known as multi-layer perceptrons, architectures that not only superseded the limitations of the original Rosenblatt design, but they evolved to the point of being applied with great success in areas so complex such as artificial vision or voice recognition. Also, it's necessary to point out that the performance of the computers in this stage at this time would not allow the training of complex algorithms. That evolution, uh, all that evolution that has taken neural networks into what they are, has required, of course, the adequate technological evolution, and not only in the algorithms used, but in the um, performance of calculation, memory, and other stuff. So, sigmoidian neurons. Frank Rosenblatt's artificial neuron was activated when the ponderated summation of the values of input was superior to a certain threshold. We saw that we could express this behavior using the following expression. So its output equals 1 if the sum of the input times the threshold is greater than the threshold, and if this is false, it's 0. So this expression can be simplified in one of two ways. The first one is getting the threshold to the left side of the inequality. Even when it's with a negative sign, we can simplify this by adding minus threshold and calling it simply B, as in bias. In this way, the previous expression would be reduced to output equals 1 if the sum of the input times its weight plus B is greater than 0, otherwise it's 0. Interesting. So let's remember that B would be the threshold, but the negative threshold. So with these changes, we could show the artificial neuron as follows. So we have B, that is the negative threshold, the summation, the inputs, the weights, and the step function. Cool. And this structure in which the step always situates the 0 value because the threshold is added to the ponderated summation of the input values. The second simplification references the product of the input values and weights. Let's remember this before the concept of scalar product. Oh no, vectors. This is horrible. Or maybe not. Oh yeah. Vectors. Without pretending to go too much in excess into the mathematical interpretation that is behind these concepts, we understand as a vector as any mathematical entity that we can imagine as a straight line in a space of n dimensions. For example, a space of only one dimension, that is, one segment, a vector could be shown in the following way. In a space of two dimensions, that is, a plane, a vector could be the following. In a space of three dimensions, that is, space, a vector could be shown as follows. Cool, x, y, and z. And that's how we could keep on going into spaces of greater dimensionality. Although it would certainly be much more complicated to show it, even, or maybe even impossible. In any case, we can see that a vector is determined by its coordinates in space, in the space in which it has been defined. So in the space of two dimensions, we can see that the coordinates of the vector v are vx and vy, and the projections of v over the axis of our space. And the space of three dimensions shown in the last image of the coordinate of the vector v have as coordinates vx, vy, and vc. Again, the projections of the vector over the axes in the three-dimensional space. That is, we can express our vector as an ordered succession of coordinates, as an ordered set of coordinates, I think. So v equals vx, vy, vc. In Python, we have a lot of ways to create a variable that represents a vector, but without a doubt, the most appropriate one is using a multi-dimensional numpy array. For example, import numpy as np, a equals np the array 4, 1, 2, a. Array 4, 1, 2. Nice. Scalar product of two vectors. The scalar product of two vectors is a function that is applied to two vectors, and it returns one number. It does not return a vector. Wow. This function is represented by a dot. That's right. The scalar product of vectors a and b is represented as a dot b. In a Euclidean space, the result of the scalar product coincides with the product of the modulus of the vectors. That is their longitude or their length, and the cosine of the angle that they form. So a dot b equals length of vector a times length of vector b times cosine of theta. In the aforementioned expression, the small dot represents the multiply operation. If we express vectors a and b in function of their coordinates, the scalar product coincides with the summation of the products of those taken 2 into. That means a dot b equals ax times bx plus ay times by plus AZ times BZ. We can observe that the scalar product result of two vectors is independent of the order in which they are considered. That is, A dot B equals B dot A. So the algebraic expression of an artificial neuron. Let's remember the last diagram that we saw of the artificial neuron. So we have the B, which is the negative threshold. We have the xi inputs, and we have the wi weights, which are multiplied by the inputs, then go to the summation, and then go to the step function. So the result of the ponderated summation, which we already know, adds up each entry value xi times the weight of the linked weight. Sorry, times the weight. Just times the weight. Plus the bias. So let's call this result Z. So Z equals W1 times X1 plus W2 times X2 plus W3 times X3 plus W4 times X4 plus B. Wow, that looks awfully lot like the scalar product. Now, if we consider the set of values, of input values of the now if we consider the set of input values of the neuron xi as a vector, we have the x equals x1 comma x2 comma up until xn. And if we consider the set of weights as another vector, we have w equals w1 comma w2 comma up until wn. We can reach the conclusion that the ponderated summation can be also expressed as the scalar product of the vector composed by the weights and the vector composed by the input values, and then of course plus the bias. So Z equals w dot x plus b, which allows us to algebraically express the behavior of the neuron, therefore in the following way: output equals 1 if w dot x plus b is greater than or equal to 0. Otherwise, it's 0. So just remember that the dot product is the same as the scalar product. Dot product is the same as the scalar product. So it's pretty interesting actually. Now I understand what linear algebra is involved. So, activation function. Frank Rosenblatt's neuron, as we already know, applied a step function to the result of the summation of the scalar product of the values of the input values and the weights and the bias. So we'll will see ahead that the use of the step function supposed important limitations that took a while to be resolved. One of the first activation functions that were used to substitute the step function was the sigmoid function, defined by the following expression. That is sigma of x equals 1 divided by 1 plus e to the power of negative x, whatever that means. And we can represent it in the following graphic as follows. Cool. So we demonstrate that for values very negative of x, the function is the function approaches 0, and for very positive values of x, the function approaches the value of 1. And well, as we've seen, the input to the activation function, that is the result that we've called z in the previous section, is given by the expression w dot x plus b. The sigmoid neuron will return the result of applying the sigmoid function to this value. That is, the output will be equal to the sigmoid function of the z value, which is w dot x plus b. Now, the schematic of these kinds of neurons will therefore be, well, it's the same thing, just instead of the step function, we use that. Being the only change in respect to the last scheme seen in the substitution of the scalar function by a sigmoid function. So, neural networks. So, in the 50s, in the time when Frank Rosenblatt was developing his perceptron, the researchers concluded that the combination of several artificial neural networks could augment considerably the capacity of the calculus. That's why, in practice, a neural network isn't formed by one single neuron, nor in general by a set of artificial neurons situated in line, but by multiple layers of neurons situated one after another. So the disposition of these layers and how they're connected between them determine the architecture of the neural network. So the multi-layer perceptron. Okay, so I just want to go back a little. So the multi-layer perceptron. The simplest architecture is the so-called multi-layer perceptron or multi-layer perceptron (MLP). Um, but we must know that the presence of the word perceptron in this name isn't anything more than a um, historical heritage, because in fact, perceptron, a multi-layer perceptron, is not formed by perceptron, but by sigmoidian neurons or by neurons with another type of activation function, that is ReLU or others, like we'll see here. So the schematic in these types of neural networks is as follows. So they're fucking crazy, man. That's a lot of inputs. So each of the circles represents with the matrices. So each of the circles represents with the nuances presented just in a little a neuron. So each of the circles is a little neuron. In this architecture, we have by convention a layer of neurons, of input neurons situated on the left that in fact doesn't really apply any function to the input values of the network. It's simply the way in which we have to indicate that the input values come from somewhere in the neural network, like to the neural network. I mean, they're not really artificial neurons, even though they're represented in the schematic as artificial neurons. So this layer of neuron receives a single input value. So these are all the input values, and then these are well, the layers that do the actual processing, and then this is um, the exit neuron. So up ahead, we have one or more layers of neurons in which each neuron is connected with all the other neurons of the previous layer. Or said with other words, the input values of a neuron um, are all the values given by the neurons of the previous layer. These are what's called the um, hidden layers. Last but not least, we have an exit layer or an output layer formed by one or more neurons in function of the analysis type that wants to be made: regression analysis, binary classification, or multi-class classification. Interesting. So, pre-fed neural networks. This type of neural networks in which the input layer is transmitted in a single direction to the exit layer without making any loops is what we call the pre-fed neural networks, or also known as the feed-forward neural networks in English. An example of these types of neurons is, well, the already seen schematic or the diagram. So yeah, they go in a single direction forward. Nevertheless, let's compare it with this architecture, in which the neurons of the hidden layer are fed back again and connected to each other. This second schematic is the one corresponding to the recurring neural networks, or recurrent neural networks, RNNs. Apart from these two architectures, there are lots, lots of them, each one with its own distinction and appropriate scenario. We'll see some of them more ahead. So these are just different architectures. So layer types. So we can distinguish three blocks of layers that we've called. So we have the entry layer or the input layer, the hidden layers, and the output layer or the exit layer. So the hidden layers receive this name simply because they are not visible, not from the entry point or the input, and not from the exit or the output of the network. Okay, yeah, this is pretty obvious. So the neural network shown in this diagram includes only one hidden layer, and the exit layer is formed by one single neuron. On the contrary, this schematic, this diagram includes two hidden layers and two exit neurons. Interesting. Okay, so neural network details. So yeah, neural networks are formed by neurons situated in different layers and connected to each other, and neurons in which the previous aforementioned schemes are represented by circles. For example, this MLP, multi-layer perceptron, has two entry or input values, a hidden layer with two neurons, and a layer with an output of a neuron. If we substitute each neuron by this diagram seen in previous sections, in which it shows the summatory function and the activation function, the result would be the following. So we have the inputs here, and they go there, and the summation with the threshold, and then the step function. And now we appreciate that each neuron has an independent behavior independent to all of them. Each of them receives a set of input values, that is a vector, calculates the scalar product of said vector and of the scalar product between the input vector and the weight vector, adds its own bias, applies the result of the activation function, and returns the final result. In general, all the weights and biases will be different. If not, why would there be so much neurons? You will only need one. So the activations functions could or could not be different. This is just depending on the library that you're using to create the neural network. Scikit-learn only allows to apply the same aggregation function to all the neurons in the hidden layers. Keras, on the contrary, allows to pick for each layer a different activation function. It can be also seen in the previous diagram how the neurons of the entry of the input layer have been substituted by the input values x1 and x2, whatever. So we'll just be from time to time going back to these diagrams to represent one or another neural network. So neural network design. Wow. When we want to create a neural network, we are obligated to take different decisions. How many neurons should the input layer contain? How many neurons should the output layer contain? How many hidden layers do we want? How many neurons should the hidden layer contain? What activation function should we use in each layer? And this is just a simple architecture for the multi-layer multi-layer perceptron. So the My Little Pony perceptron, whatever. So for more sophisticated architectures that involve another type of elements, we'll of course have to take more decisions, and it will be much more complex. But this is pretty much just the basics, man. So let's see these one by one. So the number of input neurons in the input layer. So the number of neurons in the input layer is an easy decision to take because it'll coincide with the number of values of each um, um, of each sample to analyze. So for example, if we're analyzing images of 28 by 28 pixels that represent numbers from 0 to 9 handwritten, and we want the network to be capable to identify what number is represented in each image, the layer will have to have 784 neurons, that is 28 times 28, receiving each one of the pixels of the image. And this all independently that we independently of the training data. That is, what matters is the number of values included in each one of those images. It doesn't matter how many images we have. Well, it does. It will matter for other things, of course, to how well it trains. So the number of neurons in the exit or the output layer. The number of neurons in the output layer is also an easy decision to make. It will be determined by the type of analysis we are making. So the regression analysis. In regression analysis, we want the predictive model to get us back a number representing the price that, say, a house will have in 6 months, the probability of an accident from the insurance broker, or the number of products sold across the next month, to name a few examples. In this case, the network will have only one neuron output, which value will be the one we're looking for. Of course, if we're using an activation function inside the neuron that is a sigmoid function that returns values between 0 and 1, probably will have to accelerate adequately the value returned by the neuron to obtain the real value. So, analysis of binary classification. This type of analysis, we're classifying a set of elements in two categories. That's why it's binary. For example, if an image contains a dog or a cat, if a tumor is malignant or benign, or if a person is capable of returning a loan or not, a bank loan. In these cases, the neural network will also have a single output neuron that, if we're using sigmoidian neurons, will return a value between 0 and 1, a value that will convert into a class, supposing that any value greater or equal than 0.5, for example, will have to be interpreted as class 0, and any value less than 0.5 will be interpreted as class 1 or malign and benign, etc. So, multi-class classification analysis. This type of analysis is for when we want to classify each element as belonging to a specific class among a lot, more than two, that is. For example, if we go back to our 28 by 28 images that represent numbers handwritten between 0 and 9, we want each image to be classified as belonging to the number class 0. That is, class number one or class number two, etc. In this cases, the exit layer will have as many neurons as classes. In the aforementioned example, we would need to have 10 neurons, each returning a value that will determine until what point the network believes that an image belongs to said class. We'll see it later. A way to convert these values of probabilities with the function softmax. Lost it. There we go. So design of the hidden layers. This is probably the most difficult because they don't really have a simple answer. This is, depending on the data with which we train the neural network. Some will be more convenient than others. So, in the practice, usually heuristic methods are used, like training and validating the number, testing a certain set of values for the hyperparameters that we want to determine. For example, we can validate the model generating the generated model using one or two hidden layers, each one containing 5, 10, or 20 neurons, using as an activation function the function sigmoid or ReLU. After obtaining the best result of these combinations, we could keep on making tests with close values to the best obtained to this moment to optimize the model, whatever that means. So training of a neural network. So we've said that the use of neural networks that are made up of multiple neurons ordered in different layers can, well, to say the least, put an elevated analysis capacity than, say, simply the use of one artificial neuron, of course. So let's imagine a neural network. Let's forget the architecture and let's say it's made up of hundreds or thousands of neurons. If the weights and the bias of each one are adequate, we can get so if the weights and the bias of each one are adequate enough, we can get it to work just using the values that form an image, indicating me if the answer is a dog or a cat, or that if we pass values, input values from an insurance adjuster, it indicates me the probability that said person did have or not an accident, or that if we give it the constant vital information of the patient, it gives us a probability that it's going to suffer a heart attack in the next 6 hours. So all this magic consists only and only if we have the right data. The architecture of the network is correct, and for now we'll only center on My Little Ponies. And the neurons are configured correctly. That is, if the weights and biases of each and every one of the neurons are adequate. The question that we can make is, how do we choose those weights and biases? Trying out random values? The answer to this last question is no, of course not. Independently of the number of neurons that the network includes, and considering that each weight and each bias contains a real number, any real number, the amount of combinations is just unprecedented to make a random based training. So the error function. Before we go on, let's stop a minute and try to understand how the error made by a neural network depends on the weights and the biases of the neurons. So let's say we're working in a regression environment, that is, in which we want to obtain not the classification of a sample of input, but a numerical value associated to them. And we're using a simple neural network, a multi-layer perceptron. So I'm a little pony neural network, MOP, My Little Pony, yeah. And it receives two input values, and it has a hidden layer with two neurons, and of course, because this is a regression analysis, only one exit or output neuron. So this architecture is the one we used in the previous section, and well, with the bias and the weights, it would look more like this. So yeah, it's kind of a shit show, but whatever. So let's say that initially the parameters, that is the weights and the biases, take certain values, whatever. And let's imagine now that our data, our training data is the following. It's not more than an example. I mean, this could be zoo or or whatever. X1 input, X2 input, Y output. So, yes. If we wanted to know the mistake that is being made by our network with the configuration, with the current configuration it has, for this point, for this training set, we would have to go through the predictive characteristics x1 and x2 through the network and see the result or output for each value yi. Compare it to the objective, to the target value yi. So for a concrete sample I, we could calculate the error as the square of the difference or another criteria that would matter to us. So this is just to make it positive, like in case we get negative numbers. I guess computers sometimes don't really like to work with the negative numbers. Yeah, so Ci equals the square of the difference of yi minus the other yi. So for the whole data set, the total error made, we could calculate simply as the sum of the individual errors. Yeah, so this character is wrong. The training objective would be to configure the network and choose the weights and bias values in a form that minimizes the total error made. So to make an error function, we've set as an example this neural network in which we can see that the error can be expressed in function of the neural network parameters. So let's remember what the configuration is. It still looks like a shit show. So we've given to this diagram some names to the values that each neuron returns from the hidden layer A1 and A2, A1, A1 and A2. And of course, the values returned by the adding functions z1, z2, and z3. z1, z2, and z3. And the functions of activation that, to simplify the explanation, we can say that they're all equal for now. So with this nomenclature, we can see that the output of the network y hat is to start the result of applying the sigmoid function to the z3 value. That is, y hat equals sigmoid function of z3. Let's remember that the activation function, whichever it may be, is known as a sigmoid function. The activation function is the sigmoid function. Now we can express the z3 value based on the values on which it is calculated. That is the weights W31 and W32 that multiply the values A1 and A2 respectively and the bias B3. So that is y hat equals sigmoid function of the summation of the multiplication of W31 and A1 plus W32 times A2 plus B3. And at the same time, we could express A1 and A2 as a function of sigmoid the weights of W11, W12, W21, W22 that multiply the values, the input values x1 and x2 and the biases b1 and b2. So A1 equals the sigmoid function of Z1, which equals the sigmoid function of the summation of the multiplication of W11 and X1 plus the multiplication of W12 times and X2 plus B1. And kind of the same for A2. So if we combine 1, 2, and 3, we obtain a very long equation. So we're getting back into linear algebra. Yay, boring. So the aforementioned expression can return as the prediction y hat corresponding to an input sample formed by the values x1 and x2. If we had decided that the error function were the sum of the quadratic of the differences of each prediction in respect to the real value, that is, if the mistake is given by the expression c equals the summation of the difference of I minus I squared, we have that expressing the prediction to the sample, to the yi sample, we would get the expression for, that is, the error is perfectly described by the next function. C equals summation of sigmoid function of a lot of things, being yi, as we know, the objective value or the target value or the label of the I sample, and the values x1i and x2i, two values of the predictive characteristics of the I sample. So the conclusions that we can make based upon the error function, let's remember this. So whatever it may be, whatever the structure, the multi-layer perceptron structure be, and once we decide the activation functions to apply in each neuron, we can express the error we made in an exact way as a function that depends exclusively of the weights of each link and the bias, and of course the input data. Even for a neural network as easy as we are making, the error function is relatively complex. Let's imagine a network formed up by 100 neurons and thousands of links. The expression that would define the error would be pretty unmanageable. So we could try to look for the minimum value of the function. So discarding the stochastic approach, and once we've been able to express the error made based on the network parameters, that is, the weights and biases, our objective is to find the values of set parameters that minimize the error function to our training dataset, because logically we want the behavior on the network to be the best possible. So a possible solution that we could be thinking about would be to go to infinitesimal calculus. I don't know how to say this in English, but whatever. So to explain this focus, this approach, let's say that we have a function f of x with the next graphical representation. Let's say this function shows the error we made in a neural network as with only one parameter x, a weight or a bias. So this is about an absurdly simple example, but it serves us to show us the approach, like what we would need the value to be to find of the x parameter to be, so that the error takes a minimum value. So we can see that the minimum value would be about minus 0.75 or so. So the derivative of a function in a point is the value of its slope in set point. If the function grows, the derivative will be positive. If it decreases, it will be negative. And if the function is flat on a point, its derivative will be zero. So that's what we're looking for, that the derivative be zero. Find the zeros. So in the previous image, the derivative of f of x takes the value of 0 when the slope doesn't exist, and in the value of minus 0.73 and in 0.05 and in 0.68. In this last image we can see that the f of x points are either the maximums or minimums of the function, either local or global. The derivative function of f of x, the one we can call f prime x, is a function that takes every value of x of the derivative of f of x in set point. In this case, the function that we mind, the graph of this function will be shown as follows in green, so it completely changes, as you can see. So we could identify the points of the derivative 0 or maximums or minimums by calculating the second derivative of our function f of x, that is the derivative function of the derivative function. If the second derivative in one of these points is about positive value, it's a minimum, and if it's a negative value, it's a maximum. So the method is pretty clear, and so if we have an fx function that depends only on one variable, for which we want to calculate the point that takes the lowest, that produces the lowest value, it would be enough with calculating the derivative f of x, that is f prime of x, and seeing which points this derivative takes 0, and one of these points will be the value we're looking for. But let's remember that the example we're seeing, we're assuming that the function f of x represents the error made by our neural network, and that it has only one parameter, a weight or a bias. In a real case, our function could have hundreds, thousands, or millions of parameters. In fact, most neural networks that are used today may use thousands of millions of parameters. That is a billion. Wow. And the problem with this focus is that for functions of a lot of variables, the derivative can be extremely complex, if not impossible, because it implies the calculus of partial derivatives from the function with respect to each one of the variables, and the outcome will be unmanageable. So optimizers. That's why instead of trying to apply a formula that returns us directly the values of the parameters that try to minimize the error, we need to go to methods that iteratively approximate to set values. So for this focus, let's say we're working with a neural network with two parameters, a weight and bias, or two weights, whatever. Um, it's an unrealistic example, but it's perfect to set the approach. Let's call these parameters A and B. So let's say to have an idea of how the error is affected based on the values of A and B that are chosen, we can generate a lot of um, pairs of values A, comma B that we calculate the error for, and we show the result in a three-dimensional graphic in which the values A and B are shown on the horizontal plane, and the error is the vertical axis. Yay. Everything seems to indicate that there is a combination of values A and B that generate the least error possible, and it seems like this combination is close to A equals 0 and B equals 0. The objective is to find out this combination so that the error takes the lowest value possible without requiring to infinitesimal calculus, but an iterative method that calculates these values, approximating more and more with each iteration. And this is what we call an optimization, or whatever. So we can use a gradient descent. This is an algorithm. It's not necessarily related to machine learning, or descenso de gradiente en español. And it's also known as batch gradient descent for the following reasons. If we choose a set of values A and B at random, it's possible to calculate the error that we're making. That is, if we make our training, if we pass our training data through the network, comparing the result given by the network with the label of each sample, and in our example, summing up the mistakes of all our samples. And let's say it's possible to calculate from this point the error function associated to the parameter combination A and B concretely, which is the slope of the error around the point. The metaphor that is used to explain this method is to imagine that we are in the middle of the night and we're on a mountain, and the objective is to find the place of the lowest elevation possible. If we've been put on a random place, we can always see that in some direction the terrain goes up, which we would not like to go there, because the objective is to go down. And if we look maybe the other way, it goes down, which is what we want to do. And let's say from the options that you see that go down, we can choose the direction in which the descent is more pronounced. That is, the slope is pretty steep, with the hope that it takes us to the lowest point, of course. And it does it. It will do it in the fastest way possible. So we take a step there, and we ask ourselves again, um, in which direction does the terrain go down the fastest? And we take a step there, and we each ask us until we make it to the lowest point. So let's see the same process in our example of a neural network with two parameters. We've chosen a set of values a and b at random. Let's say they're a equals 15 and b equals 20. And let's calculate the error in which in set point, and let's see the slope of the error function there, and we'll see up ahead how this calculus is made. So let's determine, for example, that there's a direction that implies a direction in the terrain, a sense in the terrain that goes up with the greatest slope possible. So the red arrow in the following image and the opposing direction in which the slope is the lowest, that's a green arrow. So in this way we modify our initial values a and b in following the green arrow. Basically, this could mean that a goes from 15 to 16 and b goes from 20 to 19. The last point we check again which one is the slope around us. And once we identify the point with the lowest slope, we can update the values of a and b again in the right direction, say to pass from 16 to 16.5 and from 19 to 18. And this process is repeated until we can no longer reduce the error. Nice. So the learning rate, critical factor in this process is called the learning rate or tasa de aprendizaje. Following the metaphor of the guy who's at night in the mountain, actually, how can he see at night? Like, he would have to feel it with his feet and his hands, but whatever. The learning rate will be the length of step that we take each time that we decide to change our position. So if we take very big steps, it's possible that we make it to a point of less altitude that we're looking, and it's possible that we may skip this point, in which case asking ourselves again where to direct ourselves, we would choose a new direction to the objective point and we could skip it again. On the contrary, if we do small, very small steps, it's more difficult that we skip the minimum step, but we will take a lot more to get there. So in practice, the learning rate is usually a very small number, like 0.01 or 0.001. So derivatives and gradients. So So let's say we take to the paper the idea of the small increments. Let's say that we are working in a neural network with two parameters a and b, in which the error function depends on this. Error equals f of a and b. So we've seen the derivative concept, but let's remember it with an additional example. So in functions that depend on only one variable, such as f of x, the derivative of f of x in a point determines the speed at which the function changes at said point. If the derivative is a point that is 0, it means that the function in said point is horizontal. It doesn't go up and it doesn't go down. And if the derivative is a point in a point is a number, a high number, and positive like 8, it means that the function is growing fast and a lot in that point. At last, if the derivative of that point is a number high but negative, like minus 9, it means that the function decreases a lot at that point. The concept of the derivative is shown graphically in the next schematic. So in this function, we've chosen 4 points, A, B, C, and D, and we've drawn in green the segments, the tangential segments to the function in said points. In A and B, the tangent is a horizontal line, which means the function in said points is horizontal and its derivative is 0 or very near 0. The tangent in the point C is an increasing line, which means that the derivative of the function in C is a positive number. In D, the tangent is decreasing, which means the derivative is negative, maybe minus 2. So gradients. Working with a function with more than one variable, the concept of derivative is translated into a gradient. So just like the derivative, the gradient represents the slope of a tangential line to the function pointing. The same way it occurs with the derivative into the increasing values. So to visualize the gradient, we have to look at it in 3 dimensions, of course, and we can go back to the function that we've seen in previous sections, and let's put a point in the map. Let's say our point is black and it's there. So let's say our point is A equals 15, B equals 20 or so, and now let's imagine the tangential plane to the graphic in said point. So now we can take a look at the segment that contains the previous plane and going through points in the direction of the increasing slope. The gradient is a vector that starting from our point and on the previous segment will point towards the direction of greater slope. Its modulus will be equal to the slope of the segment with respect to the horizontal plane. The greater the slope, the greater the length of the vector. So to obtain this vector, we introduce partial derivatives from the function with respect to each of the variables of the function. For example, if the function f depends of a and b, as in our example, for a point of the function, that is, for a combination of given of a and b, the gradient will be formed by the derivative of the function with respect to the variable a and times the derivative of the function with respect to variable b. That is represented formally in the following way. So gradient of f of the function a comma b is equal to derivative of a respect to f comma derivative of b respect to f. This assumes that if we have a two variable function and the gradient in a point is formed by two values, the first representing the partial derivative with respect to the a variable and the second representing the partial derivative to respect to the b variable. So if we have a function of 5 variables, the gradient will be formed by 5 values, each one for each variable. So in our example, these partial derivatives, will be defined by the slopes of the function in the point being analyzed with respect to the two dimensions defined by a and b. So this image shows in green the partial derivative with respect to the variable b, and in blue the partial derivative of the function with respect to a. As you can see, these vectors are parallel to the axis. Doesn't look very parallel to me, but whatever. Define the gradient vector. So let's see an example. So to see what all this is about, let's put on a concrete case. Let's imagine an example. Let's imagine that our example of our neural network is dependent on two parameters a and b, and we're looking for the point 10, 5. Let's say a takes the value 10 and b takes the value 5. In set point, the error is say 50. We calculate the gradient of the error function with respect to the variables a and b in the point 10, 5, and we get the vector 2, 4. The 2 means that if a increases, the function, that is the error in our case, augments. In fact, the 2 means that if a augments a certain quantity, it has to be small for it to be true. The error augments double. So the 4 implies something similar. If b increases in a certain quantity, the error increases the same quantity times 4. So by augmenting a and b, the error increases, and if we decrease a and b, the error should decrease. If by delta we understand increase, the increases to applying a and b to diminish the error could be the following: delta a equals to the derivative, to the negative derivative of f respect to delta b equals the negative derivative of f respect to b. In other words, if the partial derivative of the function with respect to the variable a is positive, it means that if we increase a, the value returned by the function increases. So if we subtract something to a, will diminish its value returned by the function. So we can subtract a, its partial derivative. If said partial derivative is very high, it means the error augments very rapidly as we augment a, in which way we could subtract a high quantity to go in the contrary direction, the direction in which the function decreases. If the partial derivative were small, it would mean that increasing a, the function increases a little. And we don't want to take a big value. So if we decrease the partial derivative, if we subtract the partial derivative, we will be taking more when the function grows more, and we will be taking less when the function takes less. Learning rate choice. Despite this, subtracting the partial derivative supposes that in any case, subtracting a quantity too big, if we're in the point in which a variable a takes the value 10, and in set point the partial derivative with respect to a is worth 7, subtracting the value 7 would suppose passing a from 10 to 3. This is a big leap of faith. We don't know the form that our error function has between such values. Maybe it has a minimum that we've been jumping through. So what we do is multiply the partial derivatives, times a very small quantity that we call the learning rate, or learning rate, concept that has already been taught. So the learning rate is worth 0.001, for example, and the partial derivative is 7. This would suppose that subtracting the parameter a, 7 times 0.001 equals 0.007. That is, a would go on to from being 10 to being 9.993. That is a tiny little step into the direction of the minimum function value. With the variable b, we would have to do the same, of course, but with the derivative in respect to b, of course, and the increments on a and b would be, of course, in the following way. So in this case, mu is the learning rate. So in summary, to apply the algorithm of gradient descent, we just choose a random point a, b, and we calculate the gradient, that is the partial derivatives of the function, with respect to both variables, and we subtract the values of a and b, their partial derivatives multiplied by the learning rate, which is supposed to be tiny, and we repeat the process until the gradient, calculated gradient, be zero or very, very small, in which case we'll be in the nearest minimum function value, or yeah, we'll be near. So the gradient calculation, the theory that is behind the gradient descent looks clear. Now, how would that apply to a neural network? So let's remember our neural network schematic. So as we've seen, the error function C depends on all of the parameters of the network: W11, W12, B1, W21, W22, B2, W31, W32, B3. The objective is to calculate the partial derivative of C with respect to all the parameters, which doesn't really seem easy considering that the function we saw links to the parameters. And let's remember once more that this example is quite simple. So chain rule, basically derivatives. So the solution to this problem is called a chain rule. This tells us that if a function f depends on the function b, g, and this one depends of the variable x, we can express the derivative of f with respect to x in the following way. So the derivative of f with respect to x can be expressed as the product of the derivative of f with respect to g times the derivative of g to respect to x, and in this case with the partial derivatives the rule is basically the same, and this rule can be applied iteratively. So the function f depends on the function g depends on the function h, function j depends on the function x. We can calculate the partial derivative of f with respect to x in the following way. So a derivative of a sum of functions. So more maths, very useful. The derivative with respect to x of a sum of functions is equal to the sum of the derivatives of each function with respect to x. You didn't know calculus, now you know calculus. Yay. And of course the same thing applies to partial derivatives. And this is of course especially useful since we define the error of our network as a sum of errors for each of our data sets. So if we want to calculate the formula of a partial derivative in this function, in this cost function with respect to a parameter, we can simply consider the cost function for a single sample instead of doing the whole sum, and calculate the partial derivative of this function with respect to the parameter, and do the sum later. So we can apply these ideas to the partial derivative um, with respect to a weight and a bias. So let's do it with a bias. Partial derivative with respect to, sorry, not to a weight. Partial derivative with respect to a weight. So going back to our network, if we have the function of the cost function c equals the sum of the quadratic of the difference between hat yi and yi equals to the sum of ci, we could start by calculating the partial derivative of ci with respect to W31 if we take into account that ci depends on the prediction of yi, and this prediction depends on Z3 and Z3 depends on W31. We could apply the chain rule in the following way. So the derivative of ci with respect to W31 will equal the derivative of ci with respect to yi times the derivative of yi with respect to z3 times the derivative of z3 with respect to W31, and the functions ci, hat I, and z3 are known and expressed with respect to hat yi, z3, and W31 respectively. So ci equals the square of yi minus hat yi. Hat yi equals sigmoid function of z3, and z3 is equal to a1 W31 plus a2 W32 plus b3. And if we calculate the derivatives, the partial derivatives that we're interested in, we use the chain rule and the whatever rules. And we put everything together, we get the following expressions, and fortunately all these values are known. That is the prediction hat yi, the target value yi, the derivative of O, because it's a known function as a sigmoid, and the value a1 returned by the neuron 1. Okay. So now the partial derivative with respect to the bias. So if we apply the same process to the calculus of the partial derivative of the function, the cost function with respect to bias b3, we get the next result. So the derivative of ci with respect to b3 equals the derivative of ci with respect to hat yi times the derivative of hat yi with respect to z3 times the derivative of z3 with respect to b3. And the equations that link these values are exactly the same ones. The only thing that changes is the derivative of z3 with respect to b3, which is apparently 1. So that means that the final derivative of the function of the cost function is even cleaner than in the weight. So now we apply the chain rule. So once we get these partial derivatives, we can use the chain rule again to go through the neural network from right to left, calculating the rest of the partial derivatives. So if we wanted to calculate the partial derivative um, of the cost function for ci with respect to a1, we could do it applying the chain rule. If we take into account the relationship between a1 and z3, and we can calculate the partial derivative of c3 with respect to a1, and so on. And we can remember that to obtain the function of total cost, it would only take to sum all these functions, and the result of this process is a very boring thing. And if we call this result a partial gradient, the sum of all the gradients of the partial gradients makes up the gradient, or the gradient vector of the cost function, vector that points, as we've said several times, in the maximum direction of the function, in this case the error function. This vector is the gradient of the function, of the cost functions for all the dataset samples with which we've been training our neural network. And as we can see, this is the iterative calculus that goes through the network from right to left, and gives the training method back propagation, or retropropagación en español. So the training process. Let's see then the training process for a multi-layer perceptron. Initially, the parameters, weights, and biases, that is, are initialized with some values, typically random values. Then all the samples from the dataset are entered through the network one by one, obtaining predictions for each one of them. Each sample obtains the partial gradient of the function of the cost function to it. That is the set of partial derivatives with respect to each and every one of the parameters. Once obtained, once all the predictions are obtained, the total gradient is calculated based on the cost function as a sum of all the partial gradients, and each parameter is modified from the network by subtracting the product of the derivative of the partial derivative of the cost function, which corresponds at the learning rate. And at this point, the network is configured in a way that the global error is something inferior than what existed before. So logically, if we take all the data through the network before calculating the gradient function, the error gradient function, and we modify the parameters based on the learning rate, we will have advanced a little in the minimum direction. But we will have to repeat this process until we get close enough to something that we like. And each time all our data goes through the network, we say that we've completed an epoch. So That is, it will be a lot of epochs before the training process of the neural network uh, reaches its end. So, other optimizers. These algorithm um, is what we've denominated a gradient descent or batch gradient descent algorithm that in every data of our data set of our training data set will have to go through the network before they get modified, before the parameters based on the gradient function are modified, which are based on the error obtained function. And with this approach, the calculated gradient is the one that better reflects the modifications to apply to the parameters to improve the global error, that is, to descend across the surface of the error function by the best path possible. But it has a disadvantage. The number of necessary epochs is, of course, elevated. Wow. And the necessary time to complete each one of them is also that it requires considering all the dataset um, samples. So in general, it is gonna be a long time. So before you see results. So other optimizers have been developed, also based on gradient descent. So we have a stochastic gradient descent. The optimizer stochastic gradient descent or descent sobre de gradiente estocástico simplifies the calculus considering only one sample shown and to calculate the gradient and then to update the parameters. That is, we only use one single sample. We calculate the function error and on top of that the gradient and the increments to each parameter that just decreases so much more because the algorithm will go to the minimum in less coherent manner in each iteration. But of course, it's much more difficult to not realize that we're in a local minimum. So yeah. So we also have mini batch gradient descent. Another alternative is the mini batch gradient descent. If if the regular gradient descent takes up a lot of resources, even if it returns the best error function result, and the stochastic gradient descent only takes one sample, but is the fastest and but the one prone to error making. Why not make an intermediate solution? So mini batch gradient descent is basically this. It calculates the gradient not from all the set of training, not of a single sample, but a small set, random set called mini batch. So this, of course, takes up less time, but it, of course, again, has the possibility of landing in a minimum local more easily. So let's take into account that this approximation mini batch often gets named stochastic even when it involves iteration. In other words, when we read the term stochastic gradient descent, we must take into account that very probably it refers to a mini batch stochastic gradient descent. So, momentum. So, stochastic gradient descent with momentum, or simply momentum, remembers the increment applied to the parameters each iteration and determines the next update like a linear combination between the increment of the actual iteration and the previous iteration. That means that it applies increments with a certain inertia. So there's also the Nesterov accelerated gradient, modified version of momentum, and a nag. This algorithm also adds the inertia, but it tries it attempts to decrease the increments when the algorithm is getting closer and closer to the minimum. ADAGRAD, Adaptive Gradient Algorithm, or Algoritmo de Gradiente Adaptativo, is a modification of the stochastic gradient descent in which different learning rates are used for the variables, having into account the accumulated gradient in each one of them. The problem with this optimizer is, of course, that on occasion it can occur that the learning rate for a variable decreases too quickly due to the agglomeration of high values in the gradient at the start of the training, which could lead to the training not being able to approximate to the minimum in said dimension. So there's a document here if you want to read it. So RMS prop. So RMS prop, or group mean square propagation, is a variation of ADAGRAD in which instead of maintaining an accumulated of the gradients, the concept window is used to consider only the recent gradients. ADAM, or Adaptive Moment Optimization, combines the methodology of momentum and RMS prop, calculating linear combination between the actual increment, the current increment, and the previous increment, and considering the most recently appearing gradients in the updates to maintain different learning rates per variable. So optimizers, that's a deal. It really does change everything. So we're gonna see how they work and in various situations. So large valley SGD momentum nag ADAGRAD adult RMS prop. So we can see that SGD loses. So Beal's function. In this second case, all the optimizers are capable of finding the minimum even when the SGD is much slower than them, and momentum and nag, due to the big impulse because of the momentum, they take a while before finding the right direction. So saddle point. So multi-layer perceptrons. As it's been told before, the architecture of the My Little Ponies multi-layer perceptrons is the simplest one. It's about feed-forward networks in which we have an entry layer or an input layer, one or many hidden layers, and an exit or output layer in which the information flows from the entry to the output without any loops or communications between neurons from a same layer. So, of course, we have the classic diagram. So, let's create a My Little Pony multi-layer perceptron using the scikit-learn library and apply it in a simple scenario of image classifications just after a simple bathroom break. Okay. So the mnist database. The mnist database is considered the hello world of artificial vision. It contains a training set of 60,000 images of handwritten digits. So 0, 1, 2, 3, 4, 5, 6, 7, and 8 and 9. Let me know if I'm missing one. And another set of tests with 10,000 additional samples. So, as explained on the website, the original images were normalized in such a way that they fit in a 28 by 20 in a 20 by 20 pixel grid, maintaining the proportions of the original image. And so the ending up in a 28 by 28 grid. These modifications are where the M comes from. So it's the Modified National Institute of Standards and Technology database. The samples included in the training set were the result of scanning a digital manuscript of scanning digit manuscript, of 250 people, including high school students and employees of the Office of the United States Census. The sample dataset contains scan digits of another 250 different people with the same profiles, which allows to ensure that the model obtained is capable of interpreting digits, even of people not involved in the generation of the data of training. In this case, in this tutorial, we'll work exclusively with the training set, applying the cross validation or holdout, whichever is better. And you can download the file that we'll be working with here, and you'll have to decompress it or read it from pandas, indicating that it's a zip compressed file. So let's download it. So cool, bro. Cool. Okay, so we're gonna read the mnist dataset, and we're going to put it in a data frame pandas and show the first of the digits using matplotlib. We're going to import both libraries, pandas as pd and matplotlib.pyplot as plt, and then we'll read the file, and you will have to have decompressed it with unzip, just like I did. Unzip mnist.zip in your working directory. That should generate a mnist.csv file for you. And then, well, we read the file. No header and data.head. Okay, let's try that. So of course make sure you have all the dependencies installed. Okay, so I'm going to see if I can install Jupyter Arch Linux. so I'm back. Okay, so we got an empty float, 0.8